Okay, welcome back. So we will continue with our discussion on laminar boundary layers. So just to give a quick recap, in the previous class, we looked into finding out the boundary layer thickness using something known as the momentum integral approach. And we saw that the very concept of this approach relies on certain things. For instance, first assuming a typical form of the boundary layer where, all the boundary conditions, typical form of the velocity profile inside the boundary layer where the velocity profile is just not simply an ad hoc profile that we take, but it basically satisfies the boundary conditions as we saw. For instance, we solved a problem where we looked into a third order velocity profile, and we saw that the constants can be derived by using the boundary conditions at the plate surface and at y equal to delta. Okay, so once we know the velocity profile, so the powerful thing about this momentum integral approach with respect to the Blasius solution, which I said is the most exact way of finding out the velocity profile. But since the momentum integral equation is simple, I mean it's I would say relatively simple with respect to the Blasius solution. The its central core lies on the fact that we have the knowledge of the velocity profile, and because of that velocity profile is known, we can what we use the momentum integral equation, which relates the momentum thickness to the wall shear stress typically. Okay, so using that relation we can derive analytical form of the uh, boundary layer thickness, and we saw that the constants that appeared, first of all, before going into the constant, we saw that indeed we proved that the boundary layer thickness delta basically varies as 1 by square root of rex, where rex is the local Reynolds number. And the second thing we saw that, which was more important, is the fact that the constant that we calculate, albeit it was very close to the Blasius solution, but it shows sensitivity to the velocity profile. Okay, so this is a certain hallmark of this momentum integral approach, which you know uh, the relationship between the boundary layer thickness and the Reynolds number that we generally derive to what we know that delta by x is 5 by square root of Rex in case of the Blasius solution. But here it shows sensitivity on the choice of the boundary layer profile that we take. Okay, so to elucidate further, we will look into one more example where we consider, as you can see on your screen, we consider a 2D laminar boundary layer flow. But this time, we instead of taking a polynomial profile of u by u infinity, we will consider a sinusoidal profile here. And rest assured, here we'll not bother about calculating the constants in the boundary profile, because the bound in the velocity profile that we consider here, for instance, this profile, you can see that the boundary conditions are trivially satisfied here. For instance, at y equal to 0, I know that my velocity is u equal to 0, and that indeed is the case because at y equal to 0, this term vanishes. Okay. Similarly, at y equal to delta, you can see that u equal to u infinity because sine pi by 2 is equal to 1. And you can also show that del u by del y at y equal to delta is 0. Why? Because if you differentiate this, if you differentiate this with respect to cos, okay, so you'll basically get y. So what will you get? Okay, you will get pi by 2 delta times cos of pi by 2 y by delta, and then I need to substitute y to be equal to delta, right? Which means I get cos of pi by 2, meaning that it's 0, which means the boundary conditions are also satisfied. Okay, so as I said, the velocity profile, although it's an assumption that we take that the velocity profile follow this form is just not ad hoc, and it indeed satisfies the boundary condition. Okay, so now in this given question, what we'll do is we will see that what if we take a sinusoidal profile and then try to evaluate the boundary layer thickness. Okay, that's the first task that we will do today. And the second thing is, once we know the boundary layer thickness, okay, we can also calculate something known as the displacement thickness. And when we calculate this, I will actually tell you the physical significance of this displacement thickness. And thereafter, once this displacement thickness is also calculated, we will look into the expression of the drag force, and we'll try to estimate how much the drag force will be. I mean, how much will be the drag force that the plate experience due to the incoming fluid, which is coming at u infinity. Okay. Given that being said, the length of the plate is given as L and its width is given to be equal to B. Okay, so these are the three things that we will try to evaluate here. And let's proceed step by step. So first of all, what we'll do is, given this velocity profile, we will try to calculate the boundary layer thickness delta as a function of x. Okay, and indeed we will see that in the constant that we get, that is delta by x equal to some constant by rex, that constant will now depend on the choice of this velocity profile inside the boundary layer. Okay, so needless to say, we will use the momentum integral approach. So let's calculate the solution for step 1. Okay, so solution to part 1. So we have, so for instance, the velocity profile is u by u infinity equal to sine of pi by 2 times y by delta. That's the velocity profile that we had. And indeed, as I said, you can see that at y equal to 0, my u becomes to be equal to 0. The second is at y equal to delta, my u becomes equal to u infinity. And also you can prove that at y equal to delta, your del u by del y at evaluated at y equal to delta, this is simply equal to 0. Okay, which means that the boundary conditions are indeed satisfied, and this clearly means that this profile, okay, so this profile can be chosen as a legitimate velocity profile inside the boundary layer. Okay, all right. So once the profile is figured out and we can say that, okay, this can be a legitimate profile inside the boundary layer, our next task, remember, is to calculate the boundary layer thickness delta. And as you know, for this we will use the famous momentum integral relation. So we'll use the momentum integral relation, and let's see what does it say. So we know that it says it, so basically it gives the relationship between your wall shear stress to the incoming flow velocity. That's the ratio that you get. For example, it speaks about tau w by rho u infinity squared. And I hope you realize that this tau w is the wall shear stress, which basically takes into account the dissipating effects of the flow. Okay, while this rho u infinity square, maybe if you could add a half, you can sense that this is something related to the incoming kinetic energy of the fluid that is flowing. Okay, so this ratio, as we know, this is equal to your d theta by dx, where we know that my theta is the momentum thickness that we want to, you know, evaluate. This theta is the momentum thickness. Okay, so that's it. So let's maybe evaluate. I need to maybe charge a little. So sorry for that. I just need to charge my pen a little bit. Just spare me some couple of minutes. Let's charge them up. Just give me a couple of minutes, guys. I just need to charge my pen. I just need to check this. Okay, it is charges less. So just give me a couple of minutes. Anyways, so so I'll maybe I can discuss what we are supposed to do next, and I think you can guess. So what we need to do is first to evaluate tau w, and we know that u is a function of y by delta. So in principle, if you know u, that is the velocity profile inside the boundary layer, you in principle know what is the wall shear stress. And then we also need to find out an expression for theta, which is the momentum thickness. And this is something that we did in the last class as well. So for example, theta is going to be that integral 0 to delta u by u infinity times 1 minus u by u infinity. And from there, we'll try, we'll get it, basically we'll get an equation in delta and then try to solve for delta. That's the idea for getting the boundary layer thickness. Okay. Uh, just as I said, I'm just charging my pen. So just give me a couple of minutes, and till then, if there are any doubts, you can ask me. Or as I said, always, feel free to post your doubt in the discussion forum of the course as well. Okay, so I'll you know charge it periodically. So anyways, okay, let's get started. So as I was telling, the wall shear stress, which is going to be tau w, is, we know this is equal to mu del u by del y. By the way, I believe you know that actually the shear stress has got a form. If you in principle calculate the shear stress from its actual definition, it's actually, gradient of velocity. Actually, so this is basically known as the dyadic of the vector field. So it's dyadic of velocity plus dyadic of velocity, transpose. Okay, so that's what you know the actual definition of shear stress look like. But we know that in principle, since we have a velocity profile which is of the form, y by delta, this will simply, so this product will okay, so there should be a mu as well, that I believe uh, and that simply is the Newtonian relationship. So this is basically the strain. Okay, uh, and then this mu comes because of using the constitutive relation that stress is equal to strain times the viscosity, basically. Okay, and okay, so actually half of this is the strain, and we know that stress is equal to 2 mu times the strain. So that's, if you substitute, you simply get this relation. Okay, yeah, but in principle, what I'm trying to say is that this simply reduces to, mu times del u by del y. I hope this is clear to you, simply because we have a very simple velocity profile where u is just a function of, y by delta. Okay, this should be y. Oops, this should be y. Okay, and we are kind of evaluating this as y equal to 0 because this is the wall shear stress. Okay, so as I was telling, in principle, this is just an additional bit of information. This dyadic product, this dyadic of velocity plus, dyadic of velocity, transpose, this can be written as del ui by del xj plus del uj by del xi. Okay, and in principle, these quantities are tensors. Okay, as you can see, because they have two, non-repeating indices. Okay, but this simply, simplifies to del u by del y because of the very nature of the velocity profile that we have. For example, if we had a three-dimensional velocity profile containing, let's say, u, v, and w components of velocity, and each components basically have, variations along x, y, and z, then this relation won't be so simple. And in principle, then you need to calculate the entire matrix of the stress tensor. Okay, so just bear it in mind. So this definition of tau equal to mu du by dy, which we commonly call it as the Newton's viscosity formula, this is not always true in case of generic, profiles. Okay, for profiles which are 1D, you can simply use that stress is equal to mu times the gradient of velocity along the, along the, what to say, the perpendicular direction, basically, to the flow. Okay, so I'll just hint that this is something that we get upon simplification. Okay, okay, anyways, now let's evaluate this wall shear stress. So we know that my u is equal to u infinity times sine of pi by 2 times y by delta. So let's calculate what is del u by del y. So del u by del y is partial derivative of u with respect to y, and this will simply, come out to be equal to u infinity times pi by 2 delta. Okay, cos of pi by 2 y by delta. Okay, but this needs to be evaluated at y equal to 0. Okay, because we are evaluating the wall shear stress. Okay, so del u by del y evaluated at y equal to 0 is just u infinity pi by 2 delta. That is something that we get. Okay, and we will just substitute it here in this equation. So therefore, what you get is u infinity pi by 2 delta is equal to, so it's ddx of theta. So we know, and we have studied that your momentum thickness theta is, so what is theta? So your theta is basically equal to integral 0 to delta u by u infinity times 1 minus u by u infinity. Okay, and this integration is done over dy. Okay, so one important thing, you can sense that your theta is just a function of x. And the reason that is because you have already so that simple reason stems from the fact that this u we know is a function of x and y. That is clear, right? But we have already done the integration from 0 to delta along dy, which means we are kind of adding up all the y dependencies in and basically summing them into the integration, which means that now the y variation will simply go out and theta will simply remain a function of x, and that's the reason why we have a simple derivative or ddx or an ordinary derivative in despite the fact that u is a function of both x and y. Okay, because that's the very approach or the very core idea on which the momentum integral approach hinges on, is that we kind of integrate the boundary layer equations along the y direction such that we don't have any dependencies along that particular direction. Okay, so then this becomes ddx of integral 0 to delta u by u infinity times 1 minus of u by u infinity. Okay, and this is dy, which means let's calculate. So we just need to substitute the velocity profile here. So it is u infinity pi by 2 delta, and this is ddx of 0 to delta. So u infinity, we know this is a sine of pi by 2 times y by delta. Okay, and 1 minus u infinity is going to be 1 minus sine of pi by 2 times y by delta. Okay, and then this is dy. Okay guys, so I hope you can now realize that we just need to do this integration, for which we know the trick. So what we'll do is we will call this y by delta as m, which means dy is equal to delta dm. Okay, therefore this integration boils down to the fact that integral 0 to delta. Okay, so now this delta will just become 1 because we know that at y equal to 0, my m basically is 0, and at y equal to delta, I know that my m is equal to 1, and we're integrating now with respect to 1. Okay, so this is 0 to 1 sine of pi by 2m. Okay, and then this is equal to 1 minus sine of pi by 2m, and dy is going to be equal to delta dm. Okay, now we know that this delta is just a function of x only. Okay, this because this is the boundary layer thickness, so this will come outside the integral. Okay, so which means this is delta integral 0 to 1 sine of pi by 2m times 1 minus sine of pi by 2m, and then this is dm. Okay, so now what you can do is, I'll not do the integration because I believe you are experts in doing this integration. You can simply multiply this here. So you will get sine an integral over a sine function, which you know it will be in terms of cos, and then you'll have sine square of pi by 2m. What you can do is you can write sine square in terms of cos 2 theta. Okay, just by using the fact that cos 2 theta is equal to 1 minus of 2 sine square theta. Okay, so your sine square theta will simply be equal to 1 minus of cos 2 theta by 2. Okay, and then you need to integrate cos to theta, so you'll basically get cos of pi m. Basically that's exactly what you'll get, and you just need to integrate that. Okay, so that's the idea behind this integration, and I will not do this integration because I believe you guys are experts now, at least in doing this simple kind of integrations. So okay, so basically I'll tell you that this integral will get a value if you do. So once you do this integration, I have done it at my end. So this integration will give you a value 2 by pi 1 minus pi by 4. Okay, that's what this integration will eventually give you. Okay, which means I can then substitute it here. So we have what, u infinity times pi by 2 delta. Okay, and then this is ddx of delta, and the result of this integration is 2 by pi 1 minus of pi by 4, and that's it. Now, since this is a constant, this bit is a constant, and it is not a function of x, we will basically take it outside the differentiation. So this is equal to u infinity pi by 2 delta, okay, and this is equal to 2 by pi times of 1 minus pi by 4, okay, and this is going to be your d of delta by x by dx. Okay, similar to the things that we had been doing in the previous example. Okay, just I hope you realize that just the difference is the velocity profile, which basically changes the integration that we do over here. Okay, so in earlier it was simply a parabolic profile. Here it's a sinusoidal profile that we are looking for. Okay, so then let's do some simplifications. So what can we do? We'll basically take the x to the other side. So this will be u infinity by pi. Okay, uh, maybe I'll write it. Okay, it's okay, and that's fine. And then this will be 2 by pi, this factor. So 1 minus 4 pi by 4, I think I can write it as 3 pi by 4. Yeah, so this is 4 4, sorry, is this okay? Is 4 4 minus, sorry, no, I can't write this, sorry, that's a mistake. Okay, anyways, I'll just keep it at keep it as so 1 minus pi by 4, I can write it as something like this, but this won't help us at all, so just let's keep it at like this, 1 minus pi by 4, okay, and then there is going to be this dx, okay, that is fine. I think I missed a row somewhere. Let's try to see where did I miss the row. Okay. Yeah, so I think, yeah, so that's the mistake that I was doing. So wall shear stress, see the wall shear stress came out to be equal to what? So wall shear stress is this, right? But remember, tau W is mu times this. Okay, so I was doing a mistake here. So your tau W is going to be mu times this. So there is going to be a mu, which is okay. And then there is going to be this term as well, right? Okay, so that's the mistake that I had been doing. Okay, so this is going to be what? So just check it out. It should be mu pi by 2, or it should be, mu pi by rho u infinity. That should be your this thing. Okay. And 2 delta of course is anyway there. Okay, just please correct it. So this there's a little bit of correction here. So this is going to be mu pi by rho u infinity 2 delta. Okay, because I just forgot to add that rho u infinity squared basically there, and the mu of course. Okay, this is mu pi by 2 delta rho u infinity. Okay, this should be this. This is mu pi by 2 delta rho u infinity. Okay, which means I can then bring it here. I'll basically take the 2 delta over there. So this is mu pi by this term times rho u infinity. I think now it's correct. Okay. And then it is dx, and I take the 2 delta term over there. That is simply because I can then write it in terms of an integral because of this thing. So 2 delta d delta, I can simply, write it as d of delta squared. Okay. Which means I can simply now integrate this. I'll simply integrate this. So when x is equal to 0, I know that delta is 0. When x is equal to some x, arbitrarily, delta is equal to some delta of x. So then what will we get? So we'll get this as mu pi x, okay, by rho u infinity, and this is 2 by pi times 1 minus pi by 4, okay, and then this is delta squared, which means that's it. So we have some hint of how delta varies with x. Let's see if I'm doing things correctly or not. Okay, I think it's correct. Okay. So if you do some rearrangement here, and there's the simple trivial step, I'll just not do it, just like how we did in the last class. You can simply so that delta by x is going to be equal to 4.80 by square root of Rex. That's it. So you just need to try to bring this factor here. For instance, for what you can do is you can multiply, maybe what you can do is you can simply, multiply this expression and divide this expression by x, which will help you, get square root of Rex here, because we know that rho u infinity x by mu is going to be equal to Rex, okay? And then take the square root, which will give you the square root of Rex. And then since there will be an x squared, so this single x will come, which will come outside the square root, and then this thing, the square root of this quantity will simply give you 4.80. Okay, that's how this relation comes. Okay, so that's it. That's typically the relationship between the momentum, sorry, the boundary layer thickness, and which basically varies as a function of x. Okay, so again you can see this is very close to, close to Blasius's result. This is very close to Blasius's result. Okay. And the second thing is that you can indeed see that your delta basically, varies as 1 by square root of Rex, which again gives us the logical reasoning so as to why when Rex, the Reynolds number is very much greater than 1, your boundary layer thickness is typically, very much less than 1 basically. Okay. And that's also explained why within a very thin region or within a very small distance from the plate, the viscous effects are actually confined. Okay, that's it. That's the first answer. That's the which is the expression of delta. That is the boundary layer thickness. Maybe I'll stop here for a couple of minutes. You can go through it and let me know if there are any doubts. You can indeed see that the constant is close to Blasius, and at the same time, it is not also equal to exactly the constant that we got when we used the polynomial profile in the boundary layer. Okay, which again, little bit highlights, I won't say it's a shortcoming, but the what to say, it's not an exact either. That the constant is not exact, which is equal to 5 basically in case of Blasius solution. Uh, but yeah, it is very close to 5. So in principle, we can use so basically what you can do is you can also check how much is the error. So the error would be 4.8 minus or it's 5 minus 4.8 by 5 into 100. That will be the relative error between you know the result that we get from the momentum integral equation using the sinusoidal profile and the exact solution of Blasius's, okay, which uses the concept of similarity variable to solve the problem. We'll not derive the Blasius solution, but actually I'm planning to solve one question that is associated with the Blasius's profile, and we'll see that very shortly once we finish this problem. Okay, maybe I'll stop here for a couple of minutes. If you have any questions, you can ask, and then we'll go ahead and calculate the displacement thickness. Okay, all right. So I believe it's clear. So let's calculate the displacement thickness now. So before actually looking into the numerical formula of the displacement thickness, let's first try to understand what actually is displacement thickness. Okay. So for that, what we'll do is we'll consider our good old flat plate, which is having a zero inclination with respect to the first stream velocity, and we have a flow, that is flowing parallel to this plate, okay, with a profile u infinity. Okay, so what we'll do is maybe we will call a section here, and this is a section 1, and this section 1 is just taken in front of the leading edge of the plate, where at section 1 we see that the velocity profile is just uniform. That's what the section, that's what we see at this section. Okay, and then we'll also consider a section let's say maybe I'll call this some section 3 that is at a distance of some distance x from downstream to the plate, and we will also pick out a section here. Okay, now at 3, if we draw the velocity profile, we know that the velocity has to be 0 at y equal to 0, and maybe I should draw the axis here for better clarity. So this is x. So this is y. So this is y, and this is x. So if we draw the velocity profile at 3, I know that at y equal to 0, my u is 0. That is something that we have seen repeatedly. And at y equal to delta, for example, if I see that there is a boundary layer that is being growing here, okay, for example, this is the boundary layer that is growing. So I'm little bit zooming in the boundary layer. Okay. In reality, as we saw, that delta is actually very much less than the length of the plate, but I'm kind of like zooming into the portion here. Okay, just for the ease of explanation. So what I'm doing is maybe at any distance x, okay, maybe at any distance x, which is this point 3 from the leading edge, the boundary layer thickness, let's say it is delta of x. Okay. So if I draw the velocity profile at the section 3, I know that my velocity profile is going to vary something like this. I don't know the exact shape of it as of now, because you can always fit in, because we just now saw that you can always fit in certain profiles which satisfies the boundary conditions. So that profiles are perfectly fine, then good to go to serve as a velocity profile inside the boundary there. So maybe I'm drawing some random profile, but remember, these profiles are so chosen such that the boundary conditions at y equal to 0 and y equal to delta are satisfied. Okay. Now, what I do is, if I estimate the mass flux, or maybe yeah, that's it. So if I estimate the mass flux that is basically, passing through this section, okay, and I believe you understand that this section is also going to have a width, and maybe we'll call this width as v. Okay, so if I actually calculate the mass flux that is coming into this section, okay, then this mass flux is going to be, so m dot at 1 is the mass flux that is entering through this section 1, that is typically uh, the fluid that is coming in just before it enters the plate. I can tell that this mass flux is equal to what? So this is equal to the density times the u infinity, and let this height, okay, let maybe I'll call this height as h, this height as h. Okay, so maybe I'll call this height as h, and this is b. Okay, fine. I think that's. Remember, h need not be always equal to delta x. Okay, so these are two different quantities basically. For instance, if I take delta x to be here, then I know that my velocity profile is going to be equal to this, which means that it is exactly not equal to h. Although it might seem that you can take your h and delta x to be of similar here, but it's not exactly the case that h always need to be equal to delta x. Okay, but at least I know that if I pick a section here, I know that my mass flux is equal to rho u infinity h times v. Okay, that is typically your mass flux at 1. Now if I calculate m dot 3, which is the mass flux at station 3, okay, I will say that this is equal to integral, but now I know that this velocity profile is no longer equal to just u infinity, but it is a function of y basically. Okay, so what I will do is I'll pick any generic y, calculate a small strip dy, and then evaluate dm. So in principle, what I will do is, I hope you can understand that from the plate, I will pick any y, choose a small strip dy, okay, whose thickness is basically equal to dy, and then calculate what is dm through this plate, because that is done because I know that along 0 to delta my velocity profile is a function of x, which means I can no longer treat this as a constant. Okay, so then dm for this, or I can write it as dm3 dot, is going to be equal to rho times u of y b dy. Okay, that is going to be the mass flux that comes out through this infinitesimally small area at station 3. So then if I want to get the total flux at 3, I will simply integrate this. I'll simply integrate dm dot 3 from 0 to delta, which is exactly what I'll do here. So this is, so rho is constant, it will come out of the integral. It is 0 to delta u dy b dy. Okay. Now the important thing comes here. So this is your mass flux at 3. Now you pick any legitimate velocity profile inside the boundary layer, okay? Meaning that you can choose your u of y could be anything, but it have to satisfy the boundary conditions at y equal to 0 and at y equal to delta. And if you get such a profile, and if you insert the velocity profile here, you will always see that m dot 3, regardless of what velocity profile you choose, will be less than m dot 1. Okay, and that is obvious physically because at m dot 1 my velocity is uniform and it is equal to u infinity throughout. But at 3 I know that my velocity is u infinity only at y equal to delta, and more precisely it is u infinity at y equal to 0.99 times delta, which means that if I calculate the momentum through this section 3, I know, sorry, if I calculate the mass flux through this section 3, I know that my mass flux at station 3 will be always less than my mass flux at station 1. Which means what? Which means there is a loss. There is typically a loss of mass that is taking place throughout this boundary layer. Okay. There is a loss of mass that takes place throughout this boundary layer because the overall mass has to be satisfied, right? Whatever the mass that is coming in, if I pick a control volume, something like this, okay, the loss of mass and the mass that is going out has to compensate for the mass that is coming in. Okay, because the overall mass conservation has to be satisfied. Okay, which means what? Which means there along the, you know, the boundary layer, there is a little bit of mass that is not much, so long as your Reynolds number is very much high. That is not a very high quantity, but although it is not a very high quantity, but there is still a little bit of mass that is moving through this, what you say, the demarcating region between the viscous uh, and the non-viscous zone. Okay. Now, remember, we are actually looking to find out the displacement thickness. So the displacement thickness says that how much by this boundary layer needs to be shifted. This is very important. Okay. How much by how much this boundary layer needs to be shifted in order to compensate for the loss of, this mass flow rate. Okay. So by how much, you need to shift the boundary layer, okay, so that this loss of mass flow rate is compensated. Okay, and the distance, this distance of how much is known as delta star, and this happen to be called as the displacement thickness delta star. Okay, so this delta star basically accounts for the loss of mass flow rate which move outward from the viscous zone to the non-viscous zone at the boundary layer. Okay, it simply says that you need to shift your boundary layer by this much if you want to compensate for the loss of mass flow rate. And mathematically it has got the expression as integral 0 to delta 1 minus u by u infinity dy. Okay, and I believe you can simply get that this integration actually comes from the total mass. The idea of this integration basically comes from the total mass that is entering and the total mass that is leaving. That's why there is this minus sign, and so you can actually derive this delta star. It's very simple. You just take in the amount of mass coming in, you just taking the amount, you just subtract it from the mass that is going out at station 3. You will simply get an expression for delta star. Okay. All right. So that is delta star. And the question wants us to evaluate the delta star. Okay. So that's it. Then we can simply evaluate this because the velocity profile is known. So delta star is just going to be equal to integral 0 to delta. Okay. U by u infinity is the sinusoidal profile. So this is going to be, what? This is going to be equal to 1 minus sine of pi by 2 times y by delta. Okay. Times dy. And as we know, we'll do the same business. So we'll tell that my y by delta is equal to m, okay, which means my dy is equal to delta times dm, okay, which means that my delta star simply boils down to integral 0 to 1 minus sine of pi by 2m, and then we will have delta dm, but we know that delta is not a function of y, so this will be integral 0 to 1 delta 1 minus sine of pi by 2m, okay, dm. And this is rather a very straightforward integration. So what this integration will be, what, so it will be delta integral dm is m, where m varies from 0 to 1, minus this integration, so integral sign is going to be plus cos, so this is going to be equal to plus pi by 2 times cos of pi by 2m, where this varies from 0 to 1, okay. And then if you do this, this is simply going, oops, sorry, this is simply going to give you, this integration is just going to give you 1 minus 2 by pi. Okay. All right. So then your delta star is simply equal to delta times 1 minus of 2 by pi. But we know delta, right? We have evaluated delta is what? Delta is equal to 4.80 by square root of Rex. So my delta happens to be equal to 4.80x by, square root of Rex. Okay. And then this is equal to 1 minus of 2 by pi, and then this is delta star. So that's it. We have essentially, evaluated uh, the displacement thickness delta star. Okay. You can do a quick thing. What you can do is, from here you can take the ratio of delta star to delta. Okay. So if you do that, you will get that this is equal to 1 minus of 2 by pi. Okay. So this clearly says, sorry, this is 2 by pi. So this clearly says that since pi 2 by pi is less than 1, so 1 minus of 2 by pi in principle is also going to be less than 1, which means that this delta, so the ratio, this is important, the ratio of delta star by delta is actually less than 1. And this clearly means that delta is always greater than equal to delta star. Okay. And this obviously makes sense, right? Because we just need to, the delta star just says that by how much the delta needs to be shifted. And it cannot be such that delta star, see, what's the limiting case? Limiting case is that delta is equal to delta star, but this is not possible because entire mass cannot simply go out of the boundary layer in the vertical direction, which means that there should be at least some mass, okay, which needs to go out through through the section D that we just now stated. And that's also qualitatively explains why delta star, the displacement thickness is always less than the boundary layer thickness. Okay. Because remember, displacement thickness accounts for the loss of mass flow rate. You need to understand that. Okay. All right. So that's so we are done with the second part, and maybe we'll do the third part as well because that is also simple. So in the third part, they are asking us to calculate the drag force. Okay, and this is simple. So the drag. So I believe you understand that the drag force, the calculation of drag force will come from the wall shear stress. Okay, because that is what is essentially will cause the drag force. So you can think of it like that. So for the drag force, we have a finite length of the plate that is given, and maybe we'll call it as something like this, where we know that this length, the length of the plate is equal to L, and width of the plate is equal to some B. Okay, and maybe I'll draw the directions as well. So this is my X, this is my Y, and this will then be my Z. So this is my Y, this is my X, and this is my Z. And we know that there is a far field flow. There is, a far field flow that is coming, which is of magnitude u infinity, which means that maybe I'll try to draw this. Okay, so we also have a far field flow over here, which is basically, coming at u infinity. Okay. All right, and then we know that there will be the growth of this boundary layer. We know that, okay, there will be the growth of this boundary layer. So on this edge also there will be a boundary layer that is formed. On the middle also there will be a boundary layer that is formed. Okay, and I know that at a fixed x, the boundary layer profile will look, something like this. And we know that this basically will vary from 0 to u infinity. Okay, I'm not drawing the boundary layer at the different sections along the plane. Okay, so what does it mean? In order to calculate the direct force, what I will do is I will pick any distance x. Okay, I'll pick, any distance x from the leading edge, and I'll choose a small strip there. Okay, sorry. I'll basically, choose a small strip there. Okay. So what I'll do is, the idea is that I will try to calculate the differential drag force on this small strip, which happens to be equal to the wall shear stress times the differential area. Okay. So remember, the stress is basically a tensor. Okay. So if I want to get the force, I basically need to do a contraction of this tensor by something which we call it as the n hat, the unit normal basically. Okay. So here the unit normal is actually, the unit normal of this plate is actually along the y direction. Okay, so that's how you get this area coming as bdx. That's the idea, and that's the reason why we calculate this area instead of calculating instead of calculating any other area. That's why this area basically, comes into the picture. Okay, because remember, in principle we are doing the contraction of this tensor. Okay, and because this area is differential, this is going to be bdx. Okay, and we know that the net drag force will then be equal to, I need to integrate this from 0 to L. Okay. And tau W we have already calculated. This is equal to mu times u infinity delta by pi by 2 times b dx. Okay. Why? Because we know this is tau W. This is something that we already calculated. Okay. So this is del u by del y. Okay. And if you multiply it by mu, you basically, get tau W. That is the wall shear stress evaluated at y equal to 0, of course. Okay, so that's what we have written here. So that's it. We just need to substitute the value of delta. Okay, so maybe I'll take out the constants outside. So u infinity is going to be out because u infinity is just a constant. Mu is also going to be out. So mu u infinity times pi by 2b, and this is integral 0 to L 1 by delta d delta. And I know that delta by x is equal to 4.80 by square root of rex, which means what? 1 by, or maybe x by delta is going to be equal to square root of rex by 4.80, or this means that 1 by delta is going to be equal to 4.80x by square root of rex. Okay, which then means that my drag force is going to be equal to mu u infinity times pi b by 2 integral 0 to L, okay, square root of rex by 4.80x, and that's it, dx. Okay, and then you just need to use the fact that your rex is going to be equal to mu u infinity x, sorry, rho u infinity x by mu, and just need to substitute it over here. Okay, so just if you do this, if you do the calculation, I'll just skip the calculation for the sake of repetitiveness. You will see that your drag force will simply, come out to be something like this. You will see that you will get basically as 0.658 rho u infinity squared b by L by square root of REL. Okay, where your REL now is equal to rho u infinity L by mu. Okay, and if you do a little bit of simplification, you can show that this drag force, this FD, by rho u infinity squared BL is equal to 0.658 by square root of REL. Okay. And if you compare the Blasius result, I think you'll get it to be equal to 0.664. So you can see that this constant again is very close, very close to the Blasius's solution. Okay. So that's it. That's typically your drag force, right? This is your drag force exerted on the plate. Okay, that's it. That finishes this first question, which is basically it's a little bit of long, little bit of a lengthy question, but I feel this is conceptual, and I hope you can understand the things that we did in this question. Okay. All right. So then maybe I'll stop here maybe for a couple of minutes. If there are any questions, you can ask me, or else we will move on to the next question. Okay, so the next question is a little bit similar to the Blasius's result. So I mean, it is actually associated with the Blasius result, but in fact, we'll not derive it, but we'll look into something else. For example, we learned the characteristic variables, right? We learned how to non-dimensionalize and select characteristic variables and non-dimensionalize the dimensional variables. Here, the question is, as you can see, we'll try to find out that yes, we know that in Blasius solution we use the stream function approach. Then, if we use stream function, then what is the characteristic stream function in case of a Blasius's flat plate problem? Okay, that is something that we will use uh, in this case. Okay. Okay. So what we'll do is, so the idea is that so let's first write down. Okay, let's first write down the boundary layer equations. Okay, but dimensionally. So if we write the boundary layer equation, we know that there is continuity equation which is del u prime by del x prime. Remember, prime means the dimensional variable. We have been using things since our second or third class. So just remember that. And then this will be del v prime by del y prime is equal to 0. That's the continuity equation. Okay. And we have the x momentum equation. So this is the continuity equation. We also have the x momentum equation, which is u prime del u prime by del x prime plus v prime del u prime by del y prime is equal to nu times del square u prime by del y prime squared. Okay. And the y momentum equation, we know it is not so, I mean, it's important, but it doesn't relate the velocity, because we know that the y momentum equation simply reduces to the fact that del py by del y prime equal to 0, which just means that p prime is not a function of y basically. That is the pressure in case of at least in case of a flat plate laminar, I mean, at least in case of a laminar flat plate problem, doesn't vary along the y direction. In fact, you will see that even if the plate has curvature, pressure actually does not vary along the y direction, but your pressure can vary along the x direction. Okay, this is something that we'll see. So that's the only change that you witness when we have a, I mean, we don't have a flat plate, or in other words, if we have a far stream flow that is a function of x, then your pressure can be a function of x, but it cannot be a function of y. Okay. All right. So this is the x momentum. So this is the continuity. This is the x momentum, and this is the y momentum. Okay. So now the idea is that, so what we do is we define uh, So what we define something known as the stream function as u prime equal to del psi prime by del y prime, and v prime is equal to minus of del psi prime by del x prime, and where psi prime is the stream function. And of course, this is also dimensional. And sorry, dimensional. And we saw that this very definition of stream function, that u prime is equal to psi prime by del y prime and v prime equal to minus del psi prime by del x prime, this shows that the continuity equation is trivially satisfied. Okay, continuity is trivially satisfied. Why? That is because if you just substitute it here, so just substitute the value of u and v into this equation, you will see that the left hand side is also, it just comes out to be equal to 0. Okay. All right. So now the idea is that what we will do is we'll try to actually non-dimensionalize this equation and then find something known as the characteristic stream function, because the idea is that we know that we need to see what's the idea of the Blasius solution. So the idea is that we need to write the velocities in terms of the stream function. Okay, and then define a similarity variable and then solve for it basically, which eventually turn out to be an ODE. Okay. So the idea is that first of all, you need to convert your velocity field into the string function variable. Okay. So for that, what we'll do is we will try to, and then the question is asking us to calculate the what will be the characteristic string function. So first of all, what we'll do is we'll try to choose the characteristic variable that we have at our end. Okay. So for example, I know that my xc, which is my characteristic length in the x direction. So xc is my characteristic length in the x direction. We will choose this as L. Okay. Then my characteristic length in the y direction comes out to be equal to delta. See, there is a problem if you choose yc to be L, and that problem happens to be the D'Alembert paradox. Okay. The D'Alembert paradox says that if you choose the characteristic length as L, practically you will see that the plate experiences a viscous force, but theoretically you will see that the viscous term simply drops out of the, of the Navier-Stokes equation in x direction, which is a problem, right? Because this doesn't explains the actual reality, and this, and so that's a paradox, and this paradox is very famously called as the D'Alembert paradox, which then says that there should be a thin region within the, within the surface of the plate in which the viscous effects are dominant, and the scale of that thin region is equal to the boundary layer thickness. Okay, now, so this is my characteristic scale in the y direction. Okay. So if this is the case, I will choose. So you see my characteristic velocity in the x direction is u infinity. Okay. So this is my characteristic velocity in x. Okay. Then what becomes my characteristic velocity in y? So in order to calculate the characteristic velocity in y, we will look into the continuity equation. So for example, we'll define a non-dimensional u, which is a dimensional u by uc, which is u infinity. We'll define a non-dimensional x, which is dimensional x by L. We'll define a non-dimensional y, which is dimensional y by delta. Okay. So then from the continuity equation, I have del. So this is something that we have been doing, finding out the dimensional variables. So we'll be doing this fast. So this is del u prime by del x prime plus del v prime by del y prime equal to 0, which means this will be u infinity by L del u by del x plus Vc. We don't know what is the characteristic velocity in the y direction, but this is Vc by delta del v by del y. Okay. Now the point is this term is equal to order 1. This term also happens to be order 1. And I'm saying that this entire term and this entire term is equal to 0, which means if these two terms are order 1 and the overall this and this terms should in principle match each other because their sum is equal to 0, which means that the only way possible is that u infinity by L has to be of the same order of Vc by delta, which means that Vc, that is the characteristic velocity in the in the y direction, this is equal to delta by L times u infinity. Okay. So the continuity equation gives us gives us a means of calculating the characteristic velocity in the y direction. Okay, where Vc is basically your characteristic velocity in y direction. Okay, so once we do that, we can also define something known as the characteristic stream function, which is, sorry, the dimensionless stream function, which is the dimensional stream function divided by the characteristic stream function. And it is this characteristic stream function that the problem is actually asking us to solve. Okay, so that's it. Then what we need to do is we need to use the x momentum equation. Okay, I hope this is now straightforward because this is the equation that is only left. And that equation basically tells us that u prime del u prime by del x prime plus v prime del u prime by del y prime is equal to nu times del square u prime by del y prime square. Okay, and what I need to do is I will replace this u prime v prime as in basically using this. I'll basically use this in place of all u prime and v prime. Okay, so u prime is going to be equal to what? So this is going to be equal to del psi prime by del y. Okay, and then this is going to be equal to del 2 psi prime by del x del y prime. Okay, I hope this is okay. And then this is going to be equal to minus del psi prime by del x prime del 2 psi prime by del x. Sorry, this is going to be del y prime squared. Okay. All I am doing is I am just replacing the velocities with their corresponding stream functions. Okay. And then this term is going to be equal to nu times del 3 psi prime by del y prime cube. Okay, so that's it. We're almost there. So then we'll invoke the non-dimensional variable. So for instance, from here we'll get psi c by delta square L. Okay, because I know that psi prime is equal to psi. So psi prime is equal to psi by psi c. So I can write psi prime as psi prime is equal to psi times psi c. So that psi c will basically come out of here. That's exactly what we had been doing in our class when we were solving the Navier-Stokes equation non-dimensionally. So I believe you are well equipped with non-dimensionalization now, and that's exactly what we get here. And then this term would be what? So this term would be what? So this is del psi prime by del y times del square psi by del x del y. Okay. From here, I will get psi c by delta squared L as well. And then this term is going to be equal to del psi by del x times del square psi by del y square. Why? Because from here I am going to get psi c. I think I'll get psi c squared. Yeah, so this is psi c squared. Here also I'll get psi c squared because there are two psi primes here. Okay, from here I will get a L, and from here I'll get a delta square. Okay, so that's exactly what we had been getting. And the left hand side is equal to nu times psi. Hold on, I will think. Okay, yeah. So this is nu times psi c. Okay, by delta q times del psi by del 3 psi by del y cube. Okay, all right, I think that's precisely what we'll get. Okay, so what we need to do is we now need to basically, so that's the same principle that we'll do, just like the continuity equation. This is an order 1 term, this is also an order 1 term, and this is also an order 1 term, which means if they are equal, then psi c square by delta squared L should be equal to nu times psi c by delta q. Okay, that's so since these terms bear the same order of magnitude and the left hand side is equal to the right hand side, which only means that psi c square by delta square L should be equal to this term, basically nu psi c by delta q, which means I can then solve this equation for psi c. Okay, so your psi c becomes equal to nu delta squared L, okay, by delta cube, which means this is delta. Okay, so your psi c basically come out to be equal to nu L by delta. Okay. And then I'll use one of the facts. So I know that delta by L basically scales as 1 by square root of REL. This is known. And I'll just substitute it here. So your psi c can then be written in terms of the Reynolds number, which is nu by, so delta by L is 1 by REL. Okay, so this, so L by delta is going to be equal to just nu times square root of REL. Okay, and then what you can do is you can then write it as psi c. You can basically, write REL as u infinity L by nu, and then basically take this L inside this square root. So this becomes nu by nu squared u infinity L, which means your psi c is of the order of, so the characteristic stream function is nu u infinity L. So that's it. That's your characteristic stream function. Okay. So that is your characteristic stream function. Okay. So you can figure out that while you are deriving the Blasius solution, this precisely is what the characteristic stream function that you considered in your result. Okay. All right. So that's one problem associated with the Blasius solution. Okay, so I believe, so this is, so I wanted to solve it because this is a mixture of, the Blasius solution and the non-dimensional things that we have been learning. So yeah, I feel that like we can discuss this problem. Okay, so we'll solve maybe one more problem because we have time. But before that, I'll stop here for a couple of minutes. I'll just fill my mug with some water. I'll be back in 1 or 2 minutes. You can read this problem. It's a it's a simple flat plate analysis problem. You can read this and kind of devise a way of solving this problem. Okay. So I'll just come in 2 minutes. Till then you can read this problem. Okay. Let's try to solve this problem. So let's first read it. It says that water of kinematic viscosity 9.29 into 10 to the minus 7 meters square plus meter square per second, flowing steadily over a smooth flat plate at zero angle of incidence with velocity 1.524. That's given, and the length of the plate is also given. Okay, so what you need to find is the boundary layer thickness at this, and d delta by dx at that particular x location from the leading edge, and the total drag coefficient. Okay, so that's the problem. So since this is so we just need to, we were just given the values, we can simply use the Blasius's result uh, of solving for the boundary layer thickness. Okay, so for example, we can use the fact that from, so let's try to do the first part, that is calculating the boundary layer thickness. So from Blasius solution, we know that delta by x is equal to 5 by square root of rex. Okay, so what we need to do is we just need to evaluate delta, which is equal to 5x by square root of rex. Okay, so if we simply simplify, this is going to be equal to 5x by square root of rex is rho u infinity x by mu. Okay, which means I can then write it as 5 times root x by square root of you know u infinity by mu. The reason behind is that because we have the kinematic viscosity that is given, so I'll just write this in terms of nu, and then that's it. You just need to substitute your values in order to get the value of delta of x. Okay, so this will simply be equal to 5 by square root of u infinity by nu. Okay, and then square root over x. So all we need to do is to evaluate delta at x equal to 0.1524, 1.24, and we get this to be equal to 5 by square root of u infinity by nu times square root of 0.1524. Okay, and then use the fact that your u infinity is given to be equal to 1.524 meters per second, and your kinematic viscosity is given to be equal to 9.29 into 10 to the power minus 7 meters squared per second. Okay, that's what it is given. Okay, so that's it. Then you just need to substitute this in order to get the value of delta. So I believe you can do this simple substitution. Okay, now the second thing, that's also very straightforward. You were asked to find out what is ddx of delta of x. Now you know that delta of x is equal to, from the Blasius solution, this is equal to 5 by, so you can just use this bit, which is 5 by square root of u infinity by nu. Okay, root over of x. So if you do this ddx, so first of all, this is 5 by square root of nu, this will simply come out, and then ddx of x to the power half is going to be equal to x to the power 3 by 2. I think I'm correct, right? Hold on, did I do some mistake? So let's see. Okay, so since the text that is okay. Yeah, so I think this is going to be, yeah, this is fine. This should be root x. Okay, so then you just need to do ddx of this. So it is going to be equal to 1 by 2 root x. That is exactly what you're going to get. And then, you just need to substitute x to be equal to 0.154. So that's it. That's your d delta of x. Okay. And of course, the value of u infinity and nu, which we know, which basically are these values. Okay. All right. So I hope this is fine. That's just a simple, straightforward substitution problem. Okay. So the third thing is the drag coefficient. So we also need to evaluate the drag coefficient. So again, we will use something known as the spin friction drag. So the spin friction drag is equal to the ratio of tau w by half rho u infinity squared. Okay, and if you use the Blasius solution, you will get that this is equal to 0.664 by square root of Rex. Okay, now your drag coefficient is actually equal to 1 upon L. So this is an important result. So it is 1 upon, so it's kind of an average of the screen friction coefficient, kind of an area average of the screen friction coefficient. So it is 1 upon L, 0 to L, CF dx basically. That's your drag coefficient. And we know that it's 1 upon L integral 0 to L CF is equal to 0.664 times square root of Rex, okay, dx. Okay, I think this is fine. Yes, and what you can do is you just need to substitute the value of root over of Rex, and if you do the substitution, you will simply get this to be equal to 1.328 by root over of REL. Okay, and you can show that your CD is equal to 2 times of the spin friction coefficient at x equal to L. This is also one of the important result. Okay, because we know that my CF is basically equal to this, and this is 1.328. So 1.3. So if you multiply this by 2 and calculate this at x equal to L, you simply get your CD. So calculate the spin friction at x equal to L, multiply it by 2 will also give you the drag coefficient. So if you know the drag coefficient, you precisely know the drag force basically. That's one way of looking into the drag coefficient. So actually, if you pay a little bit of closer look, what you are actually doing is, so the screen friction coefficient, if I look into the flat plate, for example, maybe I'll consider this. So if I look into the flat plate here, the CF is actually defined in this. So your CF can have variations along x. Okay, for example, this is how your CF may varies. So what you are doing in the drag force is you are integrating, CF along this x. That means you are integrating at each and every CF, which is a function of x, from 0 to L, and then you are dividing by L basically. That's what you are actually trying to do. Okay, so you are kind of like looking into the average effect of this screen friction coefficient into this picture basically. Okay, I believe this is clear. Okay, so maybe we'll discuss one more problem that is associated with so this problem is associated with flow separation, where actually we witness non-zero pressure gradient in the x direction. So we have a statement. It says that the necessary and sufficient condition for flow separation to take place is the velocity profile. Is that the velocity profile must have an inflection point. The second statement says that an adverse pressure gradient is sufficient for flow separation. So you just need to tell me which of the following is true and which of the following is false. So I would say that the first statement is true, but the second statement is actually false. Okay, and I'll kind of argue why this is the case. But before that, you actually need to understand that under what condition can flow separation take place, if at all can flow separation take place in a flat plate profile. Now the first thing is that in a flat plate, flow separation actually cannot take place because you don't have a pressure gradient in the x direction. The reason behind this is because of the fact that if you apply, so what you do is, if you basically understand the momentum equation after the viscous layer, that is if you apply the momentum equation in the inviscid layer, you will see that it is basically governed by the Euler's equation, which is, so if you write the Euler's equation, so this is when we know that basically this is the region where viscous effects are not seen, or mathematically it is the region where y is greater than delta up to infinity. The flow is basically being governed by the Euler equation, which is of this form. Okay, in steady state it is v dot grad v, and this is equal to minus gradient of p. That's typically your steady Euler equation. Okay. Now, if you write this in the x direction, this simply, simplifies to the fact that u infinity times, because I know that at y greater than delta, my profile is just u infinity. Okay. So this is u infinity times, del u infinity by del x. Okay. Plus v infinity times del v infinity by del y. Sorry, u infinity by del y, because we're writing it in the x direction. And this is typically equal to 0 because I know that u infinity is not a function of y. Okay. And then we have this equal to minus del p by del x. Okay. This is p infinity. So which means this simply boils down to u infinity times d of u infinity by dx, because I know that at max my u infinity can be a function of x only. That is, u infinity is a function of x only. And this is equal to minus of del p infinity by del x. But I know that if I look into the y momentum equation, I know that del p infinity by del y is equal to 0, which means I can then write this as minus dp infinity by dx, because my pressure simply doesn't vary along y. Okay. That means p is not a function of y here. Okay. Which means that my x momentum equation outside the boundary layer simply, boils down to the fact that it is u infinity du infinity by dx, which is equal to minus dp infinity by dx. Now, for flat plate, we know this is important. Okay, for a flat plate, we know that u infinity is constant, which then means that du infinity by dx equal to 0, which then implies that dp infinity by dx is equal to 0. And that's precisely the reason why in flat plate you don't see that gradient of pressure term. Okay, because there is no force that is exerted due to the pressure gradient in case of a flat plate, typically because your u infinity is constant. Okay, but if you don't have a flat plate, for example, if you are looking into the case of a, the velocity, I mean, the development of boundary layer over a surface which is not flat. Okay, you will see that your u infinity, that is, the far field flow, will actually, depend on which location you are looking into the plate. Okay, and this means obvious, right? Because if you put your axis here, you will see a different u infinity altogether. Okay, so the development of the boundary layer here, whatever the boundary layer is going to develop, I don't know the shape, but the delta, which is a function of x, if you want to seek, you have to take care of the pressure gradient in the x direction. In principle, the term del p by del x. Okay. Now, it has been observed that if del p by del x is less than 0, this means that if I look into two sections, let's say station 1 and station 2, okay, if del p by del x is less than 0, this equivalently mean that p2 is less than equal to p1, which means that from section 1 and 2, when the fluid basically passes from section 1 and 2, it sees a favorable pressure gradient. Now, when it sees a favorable pressure gradient, it's like pressure actually pushes the fluid. So there is no chance of, boundary layer separation. But if there is a pressure gradient which is this form, that del p by del x is greater than 0, this means that p2 is greater than p1, which means that here the pressure is more and here the pressure is less. So there is, a net force which is in the opposite direction to the actual flow of the fluid, which means that the pressure gradient actually tires the fluid down, and it might cause pressure, it might cause, boundary layer separation, but it is not guaranteed to cause boundary layer separation, because see, it can so happen that the pressure gradient is tiring out the fluid, but the length is not so much, so the fluid can effectively, move through it without without basically undergoing separation. For example, this is clear if I draw a particular figure. Okay, for example, if I look into this curve plate, so you can see that, let's say from station 1 and station 2, which is this, let's say my del p by del x is less than 0, which means this is a zone of favorable of of favorable pressure gradient, which means that P1 is greater than P2, and pressure actually aids the flow that is gliding over this plate, okay? Which means I won't see any flow separation taking place in this zone of the boundary layer, okay? For example, if we draw the velocity field here, it will be nicely looking to something like this. I don't know the profile, but it will be something like this. But now if we take a zone, let's say this 3, and let's say in between these zones, my del P by del X is greater than 0, which means that P3 is actually greater than P2. So what will happen effective? So logically what will happen? Pressure will actually try to tire the flow down, which means it will try to break the flow, and it will, so then what will happen is that the flow will no longer have the strength to basically move along the surface, because additionally the surface is also providing a resistance to its motion. Okay, so it can so happen that let's say up to this distance, okay, the flow will basically be something like this, okay, because it's basically getting tired down near the, I mean near the surface of the plate, and it can so happen that at this region the flow will be something like this, okay, and going forward, let's say in this region the flow may take a turn and then be something like this. Okay, so this turn that you see in the flow, this is known as an inflection point. So this point is known as an inflection point. This is where the curvature of the velocity field actually changes. Okay, or in principle it's not the so in principle the slope changes basically. Okay, I mean the nature of the slope changes. That's something that you can say tell. Okay, which means that once you see, so if you see there is an inflection point, this means that the flow had already separated, because the flow here moves backward and the flow here basically moves upward. But let's say if we are considering the case when the length of the plate is up to this zone only. So in this zone, although there is an adverse pressure gradient, this does not mean that the flow has separated. The flow has the tendency to separate, but it has not separated, because the length of the plate is not sufficiently long that the separation, so had the length of the plate been up to here, then the separation would have taken place because there is an inflection point here. But if the length of the plate is, let's say, up to this point only, then I know that there is a pressure gradient which is tiring up the flow. There is an adverse pressure gradient, but the length is not sufficiently long enough such that you can see an inflection point. So what this means is that the necessary condition for the flow to get separate is that it must have an inflection point. But an adverse pressure gradient is not a necessary condition, but sorry, I was saying the other way around. So the sufficient condition for the flow to get separated is that the velocity profile must have an inflection point. But if there is an adverse pressure gradient, it is only a necessary condition, but it is not a sufficient condition. Okay, this is something that you need to understand basically, because let's say if I take the length of the plate to be up to here, then I know that from here to here there is an adverse pressure gradient, but the flow hadn't separated. It has tired down, I agree, but it has not separated because the direction is still in the positive, let's say, n direction. If I call this direction as n direction, n hat, it is only at this point where you see there is an inflection point basically. Okay, so once the inflection point occurs, okay, you see that the flow has separated. Okay, so the sufficient condition is that, I repeat, is that the velocity field must have an inflection point. So let's say so for example, if I give you a velocity profile and you find out that the velocity profile has an inflection point, you can rest assured be sure that there is a flow separation taking place. Okay, all right, so I believe that is clear, and this is something that I wanted to convey. So maybe that's it. That's all. So with this, we will stop our discussions on laminar boundary layer. We didn't solve problems associated with non-zero pressure gradient and non-zero U infinity, but this is the idea. You don't require much of this as far as your assignment is also considered. But we looked problems related, in particular, related to the momentum integral approach and the Blasius solution, which is like finding out, you know, like the displacement thickness, the boundary layer thickness for a flat plate analysis, and yeah, so that's that. And we also use something known as the momentum integral approach to basically calculate these quantities. Okay, uh, yes, that's it. So So that's all. That's finishes our discussion on boundary layer. So we just have one module left, and that is one of the most important module for this course, which is known as the hydrodynamic stability. From next class onwards, I will discuss, the concept of hydrodynamic stability, and maybe we'll solve one or two stability problems in the next 2 or 3 classes that are left, basically. Okay. Till then, thank you for watching these videos. As I say, if you have any doubts, please feel free to post it in the discussion forum, and we will basically, take it from there. Okay. All right. Then thank you very much. We'll meet in the next class. Thank you, guys.